Hello everybody, and welcome to the beginning of section 6.2. We are looking at page 136 in the workbook, and this section is about Gram-Schmidt and orthogonal complements. And basically, this is the study of bases for vector spaces that are either orthogonal or orthonormal. We'll talk about what that means. Turns out that having one of those properties is very special. We can do a lot of things with the basis for a vector space that has properties like that. Okay, so let's start our discussion with a definition here. So we're going to let V be an inner product space, and that just means V is a vector space that has an inner product on it. And we're going to define what we mean by an orthonormal basis for a vector space. So an orthonormal basis is an ordered basis that's orthonormal, big surprise. So let's review what we mean by orthonormal. We defined that actually at the end of the last section. Okay, so orthonormal just means that it's a basis that has two properties. The vectors are orthogonal, mutually orthogonal, and they all have length 1. Okay, so for example, if we just take the standard ordered basis for R2, that's an orthonormal basis. Okay, now technically that statement that we just wrote out is a little bit incomplete because to talk about orthogonality, we need to have an inner product in mind. And I didn't tell you what the inner product on R2 was, but there's kind of a standard assumption. If we're in the vector space Rn, the assumption is, unless the problem says otherwise, that the inner product is the standard inner product. In other words, the dot product. Okay, so by writing that statement, we are assuming that we mean that we're going to use the ordinary dot product. Okay, so with that assumption, ask yourself, are these two vectors orthogonal? Okay, well they are, because if you take the dot product, you're going to get 0. And do they both have length 1? They do. Okay, and so because it has those two properties, this is an orthonormal basis for R2. All right, let me give you one more example. We'll stay in R2. So 1 over the square root of 2 times 1, 1. 1 over the square root of 2 times 1, negative 1. That's also an orthonormal basis. Okay, and to check that, you would do the same thing that we did up above. Take these two vectors and ask yourself, is the dot product equal to 0? You can check and verify that it is. And do those vectors have length 1? You can check that they do. So there's another orthonormal basis for R2. Okay. And so in the next example, we'd like to explore just some of the properties that we have when we have a basis like that, where there's orthogonality involved. All right, so let's read this together. So again, we'll suppose that V is an inner product space, and that S, okay, consisting of V1 through Vk, is an orthogonal subset of V. That just means that all of the vectors, any two vectors in that set are orthogonal to each other, given whatever inner product we might be talking about. Okay, and let's suppose that y is some vector that's in the span of those orthogonal vectors. In other words, it's possible to write y as a linear combination of the v's. So let's start there. Okay, since y is in the span of v, we know that we can write it as a linear combination. Or I'm sorry, since y is in the span of S, we know that we can write it as a linear combination of the vectors in S. Okay, like that. Okay, and if we write it in just sigma notation, it would look like this. And we could ask the question, what are the coefficients of that linear combination? How would we calculate those? Turns out it's going to be kind of a special way that we can do that, given the fact that this set S is orthogonal. Okay, so let's make a couple of observations here. Here's the first one. So notice that for each j going from 1 up to k, we have, okay, the inner product of y with vj. We're just going to take a look at that. Okay, so it's kind of like taking the y that we have up here and just taking the inner product of it with each vector in our set S one at a time. Okay, well, up at the top here, we wrote y as this linear combination, so we can replace y with what it's equal to. Okay, so ai vi with vj. Okay, and then remember that inner products had a number of properties, including linearity properties. So if we use the first two properties in the definition of an inner product, we can take that sum outside of the inner product and rewrite it like this. In fact, this might be a homework exercise that you did recently. Okay, so that's equivalent to just writing this. Okay, and now let's take a look at the inner product that's left here, vi and vj. What's going to happen with that inner product? Well, remember that we assume that this set S is orthogonal, which means that any two distinct vectors in the set S are orthogonal to each other. And orthogonality just means that the inner product is going to be 0, so the upshot here is that that inner product of vi with vj is going to equal 0. Okay, except when I equals j. Okay, if they're the same vector, then you might remember that you take the inner product of a vector with itself, you get the norm of the vector squared. Okay, so basically every term in this sum that we have up here is 0 except the one where I equals j. And so we're going to get aj, okay, times the length of vj squared. Again, that length of vj squared comes from the one inner product that's not 0, okay, the inner product of vj with itself. Okay, so take a look at where we started and where we stopped here. We just showed that the inner product of y with vj is always equal to this. That gives us a way to solve for the coefficient aj in this expression. Okay, and so what we've discovered then, if we divide both sides by the length of vj squared, is that aj is the inner product of y with vj over the norm of vj squared. There's a formula for calculating the coefficients in this linear combination that we started with at the top, just using inner products. Okay, we're going to see that this observation that we made kind of forms the backbone of a lot of the work that we're going to do in this section.